What's good, y'all? Welcome back. In this video, we're following up with our discussion of solution templates for general linear systems problems. Remember, in the general linear systems problem, we start with a given matrix and a given right-hand side vector, and then we're looking for all input matrices X such that A times X is equal to that right-hand side vector B. Recall from the last video in this playlist, we had the following linear systems problem with a given integer matrix, not a modeling context, but a toy problem to get our head around how this works. A given right-hand side vector. Then we transformed that system into the equivalent system with a row echelon form matrix. In fact, it was reduced row echelon form because the pivots had value 1 and no other entry in each pivot column had non-zero values. This equivalent system, what we saw is solutions to that system actually solved the original system. When we were looking for solutions to the equivalent simplified system, we did so by trying to fulfill the template. Every solution to a general linear systems problem is going to look like the sum of a particular solution plus a zero solution. Before we talk about the strategy we're going to develop formally in this video, let us also formally introduce this definition. We say that a homogeneous linear system takes the form a times x equals 0. A better way to say this is a homogeneous linear system involving the coefficient matrix A is the linear system a times x equal to 0. Now, when we're looking for that x value that sends a to 0, or in our case, when we're looking for a general solution to a general linear systems problem, we call that z. The claim is, instead of focusing on the original modeling matrix A, we can actually solve that problem by looking at the equivalent problem involving the RREF form of the matrix A, u times x equals 0. Or another way to say that would be u times z equals 0. This is quite striking and requires further investigation because is it really possible that solving really algebraically hard problems becomes a lot easier just by multiplying by elementary matrices? The answer to that question is a resounding yes, and this is where we bring in the big guns. If we start with a given m by n matrix, and then we transform that matrix to its reduced row echelon form U by a sequence of left multiplications using elementary matrices, we're going to make the following claim. In fact, we've already kind of gotten our first taste of that. For any solution to the ax equals 0 problem, this matrix vector multiplication is equal to 0 if and only if u times x equals 0. In other words, solving the homogeneous linear system involving the coefficient matrix A is equivalent to solving the homogeneous linear system with the coefficient matrix U. I could start with A and I get the solutions for U by themselves, or I could start with the u x equals 0 problem. If I solve that one, I get the solutions to the ax equals 0 problem for free. As I say so often, don't trust me. I'm lying through my teeth. Confirm for yourself, and then after you've confirmed, say, okay, that guy wasn't lying as much as I thought at first. To confirm in our case, we're actually going to provide a formal, rigorous argumentation that mathematicians would call a proof. And in order to prove this, we're going to look at some of the logical structures behind it. This double-pointed arrow sign with the lines in between, that's called a biconditional statement. In a biconditional statement, it generally goes P if and only if Q. So that's kind of the template that those statements come in. When we're thinking about the anatomy of a biconditional statement, we say the proposition P on the left is true if and only if the proposition Q on the right is true. And propositions just have truth value. They're either true or false. So in this case, we would say a times x equals 0, that's going to be the proposition P. The reason that has truth value is take any n by 1 vector, put it in there, multiply it by a, it's going to either be equal to 0 or not equal to 0. So it's either true or false for any n by 1 vector. Same thing over here, proposition Q is going to be u times x equals 0, where u is the RREF form. The same value of x that we multiplied over here, we could multiply over there. It's either equal to 0 or it's not. And the statement is basically saying, if I have an x that sends a to 0, that x also sends u to 0. If I have an x that sends u to 0, that x also sends a to 0. They're identical. And you got to be a little bit careful. Not all statements are like this. For example, here is a conditional statement that only goes one way. If I live in California, then I live in the United States. The reverse is not true. If I live in the United States, then I live in California. You didn't say the magic word. In order to formally prove this biconditional statement, we're actually going to break it down into chunks. This is a quick review for those of you that have not seen this type of proof formally, or if you took the proof class a little while ago and you need a refresher. Our goal here is to prove a times x equals 0 if and only if u times x equals 0. This is the statement P, that's the statement Q. In order to do that, we're going to break it into the two separate steps. Step 1 is going to say, hey, first prove that if a times x equals 0, then it must be true that u times x equals 0. Another way to say that is if P, then Q. That's called a conditional statement. The proposition P in the P implies Q, the if P, then Q, that's how we read that, is called the antecedent. The proposition Q is called the consequent. One formal proof format that we use to prove P implies Q statements is called direct proof. And in a direct proof, what we do is we assume the antecedent to be true. We assume P is true. Then we do some mathematical work. I haven't filled it in because this is a general statement, but there's a lot of thinking that goes in. You'll see this as we do this example. After we've done that thinking, we get to a place where if we've assumed P to be true, we can conclude that Q is true. So that's called where a mathematician makes her money. Remember, our goal was to prove the biconditional statement. We broke it into the first step, which is one way, P implies Q. The second step of that proof is going to go the other way, or switch the antecedents and consequence. So instead of proving P implies Q in the second step, we'll prove also that Q implies P, at least in the direct method. To do that, we use the same direct format. We start by assuming the antecedent Q is true. We do some mathematical work from that proposition. We really think critically about what that proposition says and our background knowledge and the theorems and definitions that we've studied about that proposition. And then hopefully we get down to a place that from that sequence of thoughts, we can actually conclude immediately that P must also be true. Now that we have that proof structure in mind, let's go ahead and formally argue via mathematical proof that solving homogeneous systems involving the matrix A is identical to solving homogeneous systems involving the matrix U. We start our argument with some of the same assumptions needed for this theorem statement. First things first, we assume that we are given an m by n matrix, and then we also put that matrix in RREF form to form the matrix U. As a restatement, we want to show that any x that sends a to 0 also sends u to 0, and vice versa. The strategy for this proof is going to be to break it into two steps. The first step, we're going to start with proposition P and prove proposition Q. So we're going to start with the assumption a times x equals 0, and then we're going to show that must mean that u times x equals 0. In the reverse, for the second step, we're going to show, hey, start with u times x equals 0, and it must be true that a times x equals 0. Let's begin with step 1. In step 1, we're going to assume the antecedent. We're going to assume that a times x equals 0. So we've chosen an x that sends a to the 0 vector. Now we have to do some mathematical work to confirm for ourselves, using reasoning and previous knowledge, that this immediately implies that u times x must also be 0. In order to do that, let's recall that the RREF form comes from multiplying a sequence of elementary matrices, let's call those E1, E2, all the way to E sub t, by A on the left-hand side. Or another way to say that is the matrix U is going to be equal to A times E1 on the left, times E2 on the left, times times ET on the left. So I have this sequence of elementary matrices multiplied by A, and that gets me to U. We know more than that. We know that each elementary matrix is either going to be a shear, dilation, or transposition, each of those matrices must be non-singular. We've proven in previous lessons, go back and watch those YouTube videos, or even better, look at your notes from that the elementary matrices, each of them is non-singular. We also have a theorem from previous lessons that says that the product of non-singular matrices, the product of invertible matrices, is also invertible. So if I now take the sequence E sub t times E sub t minus 1 times ... times E2 times E1, I can form a new M by M matrix, let's call it E, as the product of elementary matrices, and that new matrix is invertible. Using that realization, I can say that in order to turn A into U, I can find, constructively in fact, a single non-singular matrix E such that E times A equal U. That matrix is, of course, the product of the elementary matrices, so it will take me some time and work to find those, as we saw in our last lesson. But the moment that I have that, what if we looked at the original equation that we assumed to be 0 and simply multiply that equation by the matrix E on the left-hand side? E times A times X, well, that must be E times 0 since A times X was 0. But I know that E times A is U, which means after this multiplication, I have U times X on the left-hand side of this equal sign. E times 0, well, E times 0 is going to be a linear combination of the columns of E, every column scaled by 0. What happens when I scale a bunch of vectors by 0? I must get back to 0, which implies immediately that U times X equals 0. This is what we meant by doing mathematical work. We started with this assumption. We thought very critically about some of the prerequisite knowledge that we brought into this, and then we've now worked ourselves down to the conclusion, starting with this assumption immediately implies that U times X equals 0. In other words, P implies Q. We're going to do the famous mathematician's trick of trying to be a lot cooler than we actually are and drop the mic. Anytime you see a mathematician write a little box at the end of her proof, it means, oh yeah, son, oh yeah, look at me, dropping the mic. Sadly, in this case, we can't drop the mic all the way to the floor. We drop it to our knee. We're only halfway done, which means I only color half that box. While the swagger was earned, we're still waiting to get to the place where the crowd cheers. To do that, we have to follow through with step 2. Step 2 was the other direction, so assume that Q is true, and then show that P must also be true. In this case, we'll say, hey, assume that U times X equals 0, where U is the RREF of A. Once we know that, we saw in our previous reasoning that the matrix U actually was a single non-singular matrix, the product of a bunch of elementary matrices, times the matrix A. The moment we know that's non-singular, we also know it's invertible. If we know it's invertible, we know an inverse exists. Let's call it E inverse, which means we could take that matrix equation that we've assumed to be true and multiply by on the left by that inverse. So now I have E inverse times E times A times X. Well, if I multiply on the left-hand side of the equation, I must also multiply on the right-hand side, so E inverse times 0. E inverse times 0 is 0. Any matrix times 0 gets sent back to 0. We know that E inverse times E, the definition of an inverse of a matrix, those two products go back to the identity matrix. And we know the identity matrix times A gets mapped back to A, which means using this reasoning, I've started with Q and I've worked down through mathematical thinking back to P. That concludes our proof. We circle the rest of this, and here we actually do kind of strut off stage and throw the rest of that mic on the ground. With that, we've actually proved this theorem that says finding solution to the homogeneous linear system AX equals 0 involving the matrix A is identical to finding solutions to the homogeneous linear system involving the RREF of A. But this has real implications for finding complete solutions to linear systems involving the matrix A, because every complete solution is going to be a particular solution plus solutions to the homogeneous linear system. This theorem has just said, if I want to solve homogeneous linear systems, work with the RREF matrix. Don't work with the modeling matrix that is algebraically complex. Another way to interpret this idea is that the linear dependence relationships between the columns of A are identical to the linear dependence relationships to the columns of U. Another way, think about this. When I multiply A times X with X on the right-hand side, I'm taking linear combinations of the columns of A with scalar multiples defined in the vector X. Any linear combination of the columns of A that gets sent to 0, that same sequence of coefficients in X will also send U to 0. Remember, that was one of the spectacular features of our last video, that finding linear dependence relationships between the columns of the RREF matrix is literally trivial. We designed that matrix in such a way that the pivots and then the non-pivots immediately are related to each other. I see that this fourth column comes from the first pivot and the second pivot, first pivot multiplied by -1, second pivot multiplied by 2. That's one of the real benefits, that finding linear combinations of these columns to get sent to 0 literally tells me how these columns are related. Moreover, when we did that, we also got the same information for the matrix A. This rigorously justifies our strategy, our approach of turning the hard problem AX equals 0 into a much more algebraically feasible or easier problem UX equals 0. Now, I'm not claiming hard and easy mean the amount of time that it takes. It still takes a ton of time to do RREF form, unless, of course, you can use a calculator. The point of this, though, is to say we take the coffee pot off the ground and put it up on the countertop. We turn hard problems into easier problems and then use the intuition that we've done in easier problems to say something very intelligent about the harder problem that we started with. Now that we have this theorem in hand, let's take a look at how to use it on a different toy example. That's what we'll do in the next video. See you there.